Hi, welcome to another episode of Learning from Home. Today, we are going to learn about electromagnetism. Electromagnetism is about the magnetic field that exists around all current-carrying conductors. Yes, if you have a piece of wire carrying electricity, there will be magnetic field around it. The first scientist who discovered this or observed this was Hans Christian Ørsted, not Hans Christian Andersen, both from Denmark. Now we can observe this today in a simple lab or in the classroom. All we need is a conductor, a straight conductor carrying lots of current, and we pierce it through a piece of paper, and on the paper we sprinkle some iron filings. And when we tap the paper, the iron filings will settle into concentric circles, and these concentric circles represent or show the direction of the magnetic field, and they are circular magnetic field lines. So we represent the circular magnetic field lines around a straight conductor by concentric circles. The closeness of the field lines near the conductor symbolizes a stronger magnetic field. When the magnetic field lines are further apart, they symbolize a weaker field. So when the distance gets further from the conductor, the magnetic field gets weaker. Next, let's learn about the right hand grip rule. The right hand grip rule tells you the direction of the current against the direction of the magnetic field. When you have a straight conductor carrying current in one direction, when the thumb points in the direction of the current, then the four fingers will curl along the direction of the magnetic field. We also need to learn the idea of the dot and the cross. In this picture here, the dot symbolizes a current or a magnetic field. In this case, it's a magnetic field coming towards you. The cross symbolizes a magnetic field that is going away from you. How do we remember that? We remember it using an arrow. When you have an arrow, the arrow tip is like a dot. So when you see an arrow coming towards you, you see the tip of the arrow, you see a dot. So when you see a dot, that means the magnetic field or the current is coming towards you. And when you see a cross, that is like the back of the arrow. So when you see a cross, that means the arrow is going away from you. So it's a current going away from you into the paper. Now, a straight current carrying conductor doesn't carry a lot of magnetic field. To strengthen the magnetic field, we have to coil the wire into many concentric circular rings to form a coil. And the magnetic field of this coil will be much stronger. We call this coil a solenoid. Now the magnetic field direction of the solenoid can also be given by the right hand grip rule. In this case, the thumb points in the direction of the magnetic field within the coil, and the four fingers curl around the direction of the current producing this magnetic field. The circuit breaker is a good example of the good use of the magnetic effect of a current. The circuit breaker cuts off the current when it becomes too dangerously high during, say, a short circuit situation. But under normal circumstances, a low current flows through the wires through the electromagnet. This produces a weak magnetic field, not strong enough to do anything. However, during a short circuit, a dangerously high current will flow through the circuit, through the wires, and through the electromagnet. The high current produces a strong magnetic field that will attract the soft iron armature down. This will then release the catch here, and this spring will pull the upper contact up, thus breaking the contact and cutting off the dangerously high current. When the electrical fault has been resolved and the current goes back to normal, then the electromagnet is no longer that strong. This spring will pull the soft iron armature back into position. So finally, to reset the circuit breaker, all we have to do is press the reset button and the plunger will push the upper contact back into position. The combination of the magnetic field of a straight current carrying conductor and the magnetic field of a pair of external magnets produces a downward force. To understand this, we must realize that on the upper part of this apparatus, the magnetic field of the external magnet goes to the right hand side. The magnetic field of the straight current carrying conductor is also going to the right hand side. They reinforce each other, producing a stronger magnetic field on top. At the bottom, the magnetic field of the straight current carrying conductor points to the left, while the magnetic field of the external magnet points to the right. They oppose each other, producing a weaker magnetic field below. There is a force going from the stronger field on top to the weaker magnetic field below. This is the working principle of the simple electric motor. The Fleming's left-hand rule tells you the direction of the force produced between a straight current carrying conductor and a pair of magnets. First, we use the left hand. We point the index finger straight ahead. We point the middle finger perpendicular to the index finger, and then we point the thumb upwards so that the three fingers are perpendicular to one another. In this case, the middle finger gives you the direction of the current, I. The index finger gives you the direction of the magnetic field, B. And the thumb points towards the direction of the force, F. Notice the thumb is the strongest finger, therefore it represents the force. The first finger, or the index finger, represents the magnetic field and it points from north to south. The middle finger points in the direction of the current. There will be questions when you are not given a current but given a beam of electrons. But remember, the direction of a beam of electrons is opposite to the direction of a current. When we have two parallel current carrying conductors, if the currents are pointing in the same direction, there is an attractive force between them. If the currents are anti-parallel in direction, there will be a repulsive force between them. We can use both the right-hand grip rule as well as the Fleming's left-hand rule to determine the direction of this force. Let's say this is current A and this is current B. Current A will carry a circular magnetic field around it. Now there are many circles, and one of those circles would be passing right through conductor B. Now if we were to apply the right hand grip rule, the direction of this current, or rather the direction of this magnetic field at this point here, is pointing this way. And so the magnetic field due to A at this point is pointing out of the paper. Now let us apply Fleming's left-hand rule to this position here. The middle finger, which is the current, points upwards. The index finger, which is the magnetic field, points out of the paper. So the thumb, which is the force, will point to the right, and that will be the force of A on B. Now we can apply the same rules to the other side. Current B will also have many circular magnetic fields around it, and one of them will pass through conductor A. At conductor A itself, by applying the right hand grip rule, this magnetic field points into the paper. So magnetic field of B points into the paper, B for magnetic field. Now we can apply Fleming's left hand rule. At this point here, the current is which is the middle finger, points upwards. The index finger, which is the magnetic field, points into the paper. So the thumb, which is the force, points to the left. This is the force of B acting on A. Notice these two are action-reaction pairs, and the forces point towards each other. This is a pair of attractive forces. Let us now apply the same rules in the case whereby the two conductors are anti-parallel. Again, let's call one conductor conductor A, and another conductor conductor B. Let's start with conductor B. If you apply the right hand grip rule for current B, since the thumb points downwards, and if you curl the four fingers, then the direction of the magnetic field due to B is pointing into the paper. Of course, we can complete the circle around it. Now we can apply Fleming's left hand rule at this point here. The middle finger, which is the current, points upwards. The index finger, which is the magnetic field, points into the paper. The thumb, which is the force, now points to the left hand side. So this is the force of B acting on A. We can do the same for the other side. Similarly, current A will produce circular magnetic fields around it, and the one circular magnetic field that passes through conductor B, if we apply the right hand grip rule, since the thumb points upwards, then the four fingers will curl in a direction that goes into the paper. So the magnetic field of A at this point here is going into the paper. Now we can apply Fleming's left hand rule at this point. The middle finger, which is the current, points downwards. The forefinger, which is the magnetic field, points into the paper. So now the thumb, which is the force, points to the right hand side. So this is the force of conductor A on B. Now notice now the two forces are against each other. So this is a pushing force against each other, and they are also action-reaction pairs. The most important application of these principles is in the DC electric motor, which is nothing more than just a pair of permanent magnets with a coil of current-carrying wires between them, plus some other apparatus like the split ring commutator and the carbon brush. We can apply the principles of the Fleming's left hand rule to understand the operation of the DC electric motor. First, recognize there is a magnetic field going from North Pole to South Pole. B for magnetic field. At this point here, there is a dot there symbolizing a current coming towards you or coming out of the paper. So if you apply Fleming's left hand rule, the current, which is the middle finger, points towards yourself. The index finger, which is the magnetic field, points to the right hand side. The thumb, which is the force, points upwards. On the other side, we have a cross symbolizing a current going into the paper. Again, we apply Fleming's left-hand rule. At this point, there is a current, which is the middle finger, going into the paper. The index finger, which is the magnetic field, is pointing to the right, and so the thumb will point downwards, so the force goes downwards. Thus, you get a clockwise movement because of the upward force on the left hand side and the downward force on the right hand side. So the motor will turn clockwise. The concept can also be explained in terms of the magnetic field lines. If we analyze this part of the region, the external magnetic field is flowing to the right hand side, whereas the straight current carrying conductor's magnetic field is pointing to the left hand side. Now this weakens the magnetic field, so the magnetic field on top is weak. At the bottom, the straight current carrying conductor's magnetic field is pointing to the right. The external magnetic field also points to the right, and so the magnetic field at the bottom is strong. Hence there's a force going from strong magnetic field to weak magnetic field, and so the force points upwards. On the other side, similarly, at the top you have the straight current carrying conductor's magnetic field pointing to the right in the same direction as the direction of the magnetic field of the external magnets, which strengthens the magnetic field on top. At the bottom, the straight current carrying conductor's magnetic field points to the left, but the external magnetic field is pointing to the right, and this weakens the magnetic field at the bottom, and hence there is a force going downwards from strong to weak on this side. Now, the strength of the motor can be increased by using stronger magnets, having more coils or more turns in the coil, increasing the area of the coil, using more current, and also inserting a soft iron core inside the coil. The soft iron core will be magnetized by the magnetic field of the coil and in turn become a strong magnet itself. Let's apply Fleming's left-hand rule on the DC electric motor. Focus on this part of the conductor. The current is now coming out of the paper, and the current is represented by the middle finger. So point your middle finger out of the paper. The magnetic field is pointing to the right. So B for magnetic field pointing to the right. So the index finger points to the right. So with the middle finger pointing out of the paper and the magnetic field pointing to the right, then the thumb has to point upwards, and hence the force is upwards. On the other side, there is a current going into the paper, while the magnetic field is pointing to the right. So again, the middle finger, which is the current, goes into the paper. The magnetic field, which is the index finger, points to the right. Now we have a force, which is the thumb, going downwards. So the force is downwards. And hence, in this situation, the coil will turn clockwise. So here we have this conductor experiencing an upward force and going up. This conductor experiences a downward force and coming down. Now, if we do not change the direction of the current, and obviously the direction of the magnetic field is not going to change, then the direction of the forces will not change. So conductor CD will continue to go up until it cannot go up anymore, conductor AB will go down and continue to go down until it cannot go down anymore. So if you let the motor turn as much as it needs to, eventually it will come to a stop with CD, conductor CD on top and conductor AB at the bottom, and then the motor will stop. Because even though the current keeps flowing, the forces generated remains in the same direction, because the direction of the force depends on the direction of the magnetic field and the direction of the current. If you don't change the direction of the current, and obviously the direction of the magnetic field won't change, then the direction of force won't change. So this conductor CD will continue to experience an upward force. Conductor B will continue to experience a downward force, and so the coil will come to a rest in a vertical position with two forces pulling against each other but not producing any moment. Thus, that is the reason why we need a split ring commutator as well as a carbon brush to allow the motor to continue to turn again and again, without which the motor will turn until the coil is in a vertical position and it will stop. The whole idea is to change the direction of the current every half round, because when we change the direction of the current, we change the direction of the force. The whole idea is when the coil is slanted in this position, yes, we want this conductor to be pushed up and we want this conductor to be pushed down. And once it crosses over the vertical line, then we want this conductor to be pushed down and this conductor to be pushed up. To change the direction of the force, we have to change the direction of the current. And so the split ring commutator does that. At first, carbon brush P is connected to commutator side X, and the current points in this direction, while carbon brush Q is connected to the semicircular half Y, and the current points in this direction. And in this situation, conductor CD goes up and conductor AB goes down. When the coil reaches a vertical position, momentarily there is no contact between the carbon brush and the commutator. So momentarily there's no current flowing through the coil. It takes inertia for the coil to cross over the vertical position over to the other side. The moment the coil crosses the vertical position by virtue of its own inertia, then there's a swap around of the contacts. Previously, P was connected to X, but now P starts to get connected to Y. Previously, Y was connected to Q. Now X is being connected to Q. And so the conductors have swapped partners. So since the current is being supplied to Q and then goes out from P, so now the current is going to go into X and it's going to flow out from Y and out of P. So in other words, now we have a reversal of current. Now the current is going to flow into X. It's going to flow into X. It's going to flow out of Y. So it's going to flow out of Y. So now the current flows opposite to where it was flowing. This reversal of current reverses the direction of force. So now what was going up can now come down. What was going down can now come up. It is important to note that as the motor coil turns, the amount of current that the conductors carry remain the same because the current is provided by the battery. If you don't change the battery, you don't change the voltage, you don't change the current in the coils. So as the coil turns, the current remains the same except during that short moment of crossover. Other than that, the current remains the same as it turns. Now, since the force depends on the current, therefore the force will not change, because force depends on the current, the magnetic field, and the angle between them. But throughout the turning, the current is always pointing in one direction. The magnetic field is also always pointing in one direction. So the magnetic field and the current are always 90 degrees to each other. Hence, since the current doesn't change, the magnetic field doesn't change, and the angle between them doesn't change, the magnetic force produced doesn't change. So what changes actually is the perpendicular distance between the two forces. It is the change of the perpendicular distance between the two forces that changes the amount of moment, amount of turning moment. And hence, when the coil is horizontal, we get maximum turning effect because the perpendicular distance between the two forces is maximum. When the perpendicular distance between the two conductors diminishes, then the turning effect also diminishes.